This talk is on Tealeaves, categorical structures for syntax, and it will be given by Lawrence Dunn. His collaborators are Val Tannen and Steve Zdanswick. Lawrence.
Thank you, thank you. I want to start with a quick poll, if you don't mind. So please raise your hand if you have ever had to use Coq to reason about substitution on any kind of syntax. That's about right. Okay, so how would you like to never do that again? That's the idea. So I'm going to set the stage a little bit and try to really nail down what problem we're trying to solve. And then I'll talk about our actual library, Tealeaves, and what we call backend libraries, which are a separate concept. And then I'll explain the workflow we have in mind. So if you want to use Tealeaves in your project, what would that actually look like? So let's start by talking about implementing formal systems in Coq. Any kind of formal system, basically anything with a precise syntax. So it could be a lambda calculus, a programming language, some kind of logic. And I probably don't need to persuade you that it's a good thing to implement these kinds of things in Coq, but it's a very tedious process. So why is it a tedious process? Well, here's the big reason. Implementing a formal system, you may have noticed, requires a lot of reasoning about syntax. And in fact, before you can actually get very far developing the meta theory of your system, you need to develop a lot of what you might call syntax infrastructure, which means you have to define the syntax of your system. You have to define a bunch of operations on that syntax. The obvious one is substitution, but there are other operations. So maybe you want an operation that computes the set of free variables of a term or something like that. And then you have to prove a lot of tedious little lemmas about these operations. So for instance, you might want to prove that under certain conditions, you can commute a substitution and a lambda abstraction or something like that. And this is very tedious. And you might say, well, yeah, it's tedious, but we can automate it. We have tools like lngin and autosubst. And that's true, but as wonderful as these tools are, it's not completely satisfying to use that much automation. It feels like there's deeper issues here. So let's take a look at this. You probably know there's a lot of different ways to represent variables and binding. And let's assume I mean like a totally concrete syntax. I'm not thinking about things like parametric higher order abstract syntax. I'm thinking about things like fully named or de Bruijn indices. And every method of representing variables, the way I look at it, is associated with two types. A type to represent variables and a type to represent labels that are on binders. So for example, if you have a fully named syntax, like with pen and paper, you represent variables with names, which are basically strings or something like that. And binders introduce names, so binders are labeled with strings as well. In Coq, you probably want to use something like de Bruijn indices, and variables there are represented with natural numbers, and binders aren't really labeled at all, they're not really labeled with de Bruijn indices, but to kind of fit this into how we view things, we'll say that binders are at least implicitly labeled with values of type unit, which is almost the same thing as saying they're not really labeled at all. And each representation has its own little operations that you have to think about and its own set of standard lemmas that you have to prove. And here is our goal. For any one of these representations, to be able to define all of those operations and prove those standard lemmas in such a way that we can apply that to any syntax. So a thought experiment. Let's say you implement the simply typed lambda calculus using de Bruijn indices. So, you know, with STLC, variables represent lambda terms. And the tricky part is you have to reason about this lambda abstraction. Now let's say your friend wants to implement the modal mu calculus. And that's a completely different system, of course. But it also has variables. In this case, they represent propositions. And you also have binders, in this case, greatest and least fixed point operations. And let's say your friend is going to use de Bruijn indices. So even though these are different systems, substitution still pretty much works the same way. And let's say you've already done this work. So how about you just tell your friend, hey, don't worry about it. I've already developed all the syntax infrastructure of de Bruijn indices. I'll just email you my vernacular files, and you don't have to worry about it. Is that going to work? That's obviously not going to work. Why not? It's not that conceptually it shouldn't work. The problem is when you defined all of those operations, you did it by structural recursion, obviously. And the problem with that is that when you structurally recurse on an abstract syntax tree, all of your definitions are now tied to the grammar of that formal system. And that prevents reuse. If you change the type that you're doing recursion on, your recursion is broken. You're going to have to tweak it. So your friend's not going to reuse your files. Your friend is going to start all over probably. So the lesson is that raw structural recursion on abstract syntax trees is too brittle. So what would we use instead? You might say we need some kind of abstract interface to use instead, and maybe we can hope to achieve a certain level of genericness in our developments. So what would that look like? Tealeaves. Tealeaves is our library, and it implements it really only does one thing. It defines a type class for data types that kind of look like syntax trees. And for this, we draw inspiration from monoidal category theory. I won't have time to go into all the details with that, but it's really cool. I would love to talk about it. If you want to talk about it after, please get in touch. Separately, we have what we call backend libraries, and these are libraries that use Tealeaves, and backends implement the theory of some variable representation. So you could have a de Bruijn indices backend, you could have a fully named backend. The one we've developed so far is a locally nameless backend, and the idea is that that library, all of its operations and all of its theorems are going to be polymorphic over this type class, polymorphic over data types that look like syntax trees. So that is the idea. Let's get a little more concrete. When we think about syntax as being parameterized by some kind of variable representation. That's two types, and it's the two types I mentioned earlier. So there's a parameter that represents variables, and there's a parameter that represents labels on binders. So just for an example, here is an inductive definition of the syntax of the untyped lambda calculus. There's nothing special about it. It does look a little verbose, and that's because we've parameterized it in this way. So you notice the var constructor accepts an argument of type var, which is one of the parameters. And the first argument to the lambda constructor accepts something, we'll pronounce that type binder. And so you would use that argument to represent like the name being introduced by the lambda abstraction within its scope. Other than that, there's nothing special going on here. The point of Tealeaves is to provide a type class for data types that look kind of like term. So I will point out, we're not trying to abstract away var and binder. Those parameters are always going to be there. We just want a more abstract definition for things that look like term. So what does that abstraction actually look like? Here is the technical part. Our main contribution is this, I think, novel category theoretic structure that we call a decorated traversable monad. Technically, this is a kind of indexed monad. And these are monads equipped with additional structure. That's really cool. And the Kleisli operation of a DTM, in other words, the bind operation, we call it bind DT in the library. This is not a very inspired name. It's bind for decorated traversable monads. If you have another name, please get in touch. And it has this kind of awful looking type. It's really not that awful. It's just verbose. And the point of Tealeaves, the library, it just implements the equational theory of decorated traversable monads. Now, let's talk about the semantics. Normally, we think about monads as capturing some sense of computations with effects. And in some cases, we think about monads as providing computations that act like substitutions. This is a more structured notion, and we think of bind dt and its equational theory as capturing something like this. You have a data structure, a decorated traversable monad, and bind dt will iterate over that data structure, and as it's performing this iteration, it will keep track of some kind of context, like the depth of the tree or something like that. And at every element in that data structure, bind dt will apply a context-sensitive substitution operation. And furthermore, when you apply this substitution operation, you can have what you might call an applicative effect, which is an idea from the literature. So this is the big theory part. Now, a Tealeaves backend to a first approximation looks kind of like this. So we'll open a Coq section, and within the scope of this section, we will assume that we have some type constructor term of 2 arguments, and we'll assume it's a decorated traversable monad. Then, remember, a term here is a type constructor of 2 arguments, one to represent variables, one to represent binders. So who chooses those types? We do, we implementing the back end. So we will choose those types, maybe we'll define those types. And when we've done that, we might be interested in, we will be interested rather, in working with this type term binder var. And we think of this as expressions. We'll give that a little notation. And we think of term binder var as any kind of abstract syntax tree where the binders have type binder and the variables have type var. So the parameter here is term. We don't know exactly what the syntax tree looks like. We don't know what the grammar of this language is, but we know it's a decorated traversable monad. And then we will define operations like substitution, and just as an example, it might have a type that looks like that. And then we will define, prove theorems about these operations, and then we'll close our back end. And when we close that back end, if you know about Coq's section mechanism, all of our operations will be polymorphic, and our theorems as well. But this is kind of a strange polymorphism. It's a little bit backwards from what you might be used to. Normally, we think about polymorphism as a kind of, I think this is the right term, data polymorphism. So think about like concatenation of lists. If you concatenate two lists, it doesn't matter what data is in that list. It just matters that you're operating on lists. Here, we're doing the opposite. It doesn't matter what the decorated traversable monad is. Any functor, as long as it's a decorated traversable monad. But we do need to know what kind of data is being stored in this DTM. Because if I'm trying to define like a de Bruijn indices substitution, I need to know that as I'm iterating over this tree, I'm encountering de Bruijn indices, things like that. So sort of I think people call this shape polymorphism, but don't quote me on that. Is there anything else I want to talk about? No, we're good. Oh, actually, you'll notice here, this is just a template, but you notice I have definition subst. We can't, normally when we define substitution, you would expect to see fixed point subst because we define things by structural recursion. We can't do that because term is not transparent to us. It's not a definition, it's a parameter. So what do we have? How are we going to define subst? All we have is this bind to dt operation and its equational theory. Okay, well, bind to dt turns out to be a very flexible operation. Lots and lots of operations that you might want to perform are actually special cases of bind dt. So for example, as you might expect, you can get a bind operation out of this as a special case. You can also get things like a fold or fold map operations, if you've heard of those. And recall, bind dt is this very generic thing. We iterate over the syntax tree. As we're iterating over the syntax tree, we remember what binders we're encountering, which is unique to every variable. And when we come across a variable, using this extra information about what binders are in scope of this variable, we'll apply a substitution, and we can have an applicative effect. So there are a lot of derived operations we can get out of this. So for example, here you can have a sub combinator that has this type, list binder times var to expression to expression to expression. So think about like functors in the fmap operation. An fmap maps some function over a tree, let's say, and it applies some function to all the leaves of that tree. Sub would be kind of like that, but on steroids. The operation that we apply to every variable is a substitution. We replace a variable not with another variable, but with an expression. And when we perform this substitution, we know what the binders are. We know that we have this list of binders that are in scope at this variable. And remember, the back end is who picks binder and var. So these are concrete types to work with. As another example, you can have a universal quantification combinator, all, which you can use to define predicates on terms. And the way you could use this combinator is by quantifying over all of the variables in a term with some predicate on terms, or predicate on variables, excuse me. And you'll notice this predicate on variables also has access to the list of binders. So for example, you could use this combinator to define what it means for a term to be closed. In other words, to not have any free variables. And you would do that by coming up with the predicate from list binder times var to prop that says something like this variable in this context of binders is closed in whatever definition you're using. It depends how you're representing variables. And by quantifying over all of the variables, you get the definition of a closed term. Another combinator would be filter. If you give me a decidable predicate on variables, then filter will give you an operation on expressions that enumerates the list of variables that satisfy that condition. Again, considered with the list of binders that are in scope. So you could use this operation to enumerate the free variables. Okay, so let's say you're sold. You want to use Tealeaves. What does that actually look like for your, if you have a syntax that you're interested in and you want to use Tealeaves? It's pretty simple. You would define the syntax of your formal system as an inductive type like this. And again, you'll notice your definition will be parameterized by binders and variables. You're just defining this type term. Then for your type term, you will implement the bind dt operation, this iteration that applies context-sensitive substitutions with applicative effects. And then there's some axioms you need to prove, the axioms of decorated traversable monads for this operation. And these axioms are actually pretty straightforward when you understand the types. So once you've done this, you're pretty much good to go. You can use any Tealeaves backend, or at least that's the idea. So we haven't implemented a Brownbackend. We've implemented a locally nameless backend, but I don't want to talk about locally nameless. So let's imagine we have a Brown indices backend, and you would import it. Import tealeaves.backends.debrown, and as a shorthand notation, you will probably want to define expression, EXPR, to mean term, unit, nat. In other words, term, where the binders are labeled with unit and the variables are nat, because the Brown backend will expect to see natural numbers for variables and units on binders. So you see, kind of, this is where the magic happens, because term is something we defined, and unit and nat are things that the backend expects. So if you do this, then if there's probably there would be an operation called the brown.substitute, and you'll be able to specialize this operation to your definition of term by getting it the decorated traversable monad instance. And you could specialize that type, and you'd probably get something like expression to expression to expression. So that's the big idea. Now, we haven't implemented an automated workflow, but we think Tealeaves could fit in very well with a workflow that uses some automation. So you know there are existing tools like lengine and autosubst that will synthesize syntax theory for you. You give it the grammar of your formal system, and it generates some definitions and theorems for you. Tealeaves is not a replacement to tools like that. It's a kind of a complementary technique, and you could use it to build tools like that. So for example, we have a locally nameless backend, and it basically proves all the same theorems as lengine generates. But our theorems are not generated. They're on GitHub. They're static. And all of the theorems are polymorphic over decorated traversable monads. So our idea is you really only need to synthesize the definition of the decorated traversable monad from a syntax, and then the user can just import a Tealeaves backend. So this workflow would use a little bit of automation, but a very principled kind of automation where you just have to synthesize bind dt and those axioms. So we have implemented a locally nameless backend, like I said. We have also implemented a multi-sorted generalization of that. It's a little hairy to use in practice, but on paper, in theory, it works very well. Just working out those engineering details is still something we're working on. We've tested this with STLC and System F. We've defined those syntaxes, and we've proved that they form decorated traversable monads, and we've used this to prove basic things like progress and preservation. And future work, we would like to generalize our locally nameless backend to work with, I can get into it. If you want to talk about the details, I can talk about it later, but a kind of multi-binder substitution, like if you had a language that had like a letrec operation, there's some details you'd have to do for that. We would like to implement a fully named backend. And like I said, we would like to give some kind of tool that can synthesize the decorated traversable monad instance on your behalf. And here's some theory, but we don't need to talk about that unless you want to talk to me afterwards. So that's all I got.
All right, we got lots of questions out in the virtual land. Any questions in the room? All right. Let's tee up the virtual questions. Just a moment.
I'll put up the theory slide in case somebody's like really dying to know, just like quick and dirty. Whoa.
we go. All right, Lawrence, have you tried to complete the POPLmark challenge with your tool? In particular, can you handle substitution for type variables inside terms?
Yes, we kind of done that with System F. I don't think we've done the full POPLmark challenge. We've done enough to convince ourselves that we could, and we've sunk our time more into thinking about. For this, I think you would have to really have a very polished multi-sorted backend. And I'm convinced you could do this. We haven't tried to implement all of POPLmark. The challenge with the multi-sortedness is we would have to formalize a multi-sorted generalization of the representation theorem for traversable functors. But I'm convinced we could. And that's on GitHub, by the way. What we have for System F is on GitHub.
Great. Next question. Does Tealeaves support representations where the type of the labels is indexed over the labels already in the contexts? Representatives that guarantee well-typedness of the term, for example.
We have not thought about this. This idea has recently come up in a conversation I had here. I've not thought about this at all, actually. I have no idea.
Okay, next question. What if your language involves several mutually defined syntactic categories? For example, call by value lambda calculus with an explicit value type. Can you still instantiate the framework for that setting?
Yes. Once again, I think this is an issue of you need a multi-sorted generalization of everything. We do have, at least on paper, a definition of a multi-sorted decorated traversable monad, which you would use if your language has multiple grammatical categories. So I think this should work just fine, yes.
Okay, next question. I'm still looking at the room if there are any questions here. Okay. How hard would it be to prove that the generated substitution is equivalent to the one defined by structural induction?
It shouldn't be hard at all, I would think. Yes, I haven't specifically tried to do that, but that should be relatively straightforward.
Sounds worth doing.
Yes.
Next question. Does your proposal support representation of the syntax of core camel, in particular with pattern matching variables being binders?
I don't know.
That'd be a great one to try.
Okay.
Next question. If I can't recurse, thank you for all the questions, R2. If I can't recurse over the syntax tree, it's not clear to me how I can define a function that computes in Coq to perform transformations like optimization on terms.
I'm having trouble picturing what that would look like.
Can you write an optimizer on your terms?
Well, you can't write a function that would actually need to change the syntax tree itself. The point is everything has to be the way we can get away with operations that are completely abstract over the grammatical details is because our operations just affect. Basically, Tealeaves is all about thinking about what happens to variables, occurrences of variables. So I'm not sure if we could do this.
So then what about functions that generate terms?
So for like a substitution operation?
Or metaprogramming or any other kind of term generating function?
I'm not completely sure. The backend doesn't have any, the backend doesn't know what your terms even look like. It's generic over DTMs. So you can define it, like the reason we can define like substitution with the Brown indices is because when I'm at a variable, I just have to make a yes or no decision. Am I going to replace this variable with some term u, or am I not going to make that replacement? I don't necessarily know what u looks like. It's just an expression. And I just have to implement the logic of yes substitution or no, don't substitute right now, assuming that this is my Brown index, and this is my list of binders, which would be, that would be the number of binders in scope. So I'm not sure. If you need logic that really thinks hard about terms themselves and their grammatical structure, that might not fit very well into our framework.
Okay, sounds like a great topic for a discussion over lunch.
Yes.
But we should move now to the next talk. Thank you.